Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, Heat Capacity of Solids, Part 1, under the paper Solid State Physics. So students, let us see what we are going to learn in this module. The first thing that we will learn is that the Dulot-Petit law is valid only at high temperatures. We learn to calculate the Phonon heat capacity. We also know that atomic vibrations are quantized in Einstein model and that the motion of each atom is described by a harmonic oscillator. We are also able to find expression for energy and Phonon occupancy number. And we also further learn that according to Einstein model at low temperature, specific heat decreases exponentially, unlike experimentally where specific heat is directly proportional to the cube of the temperature. In this module, we learn the contribution of lattice vibrations to the thermal properties of the solid using the classical and Einstein model. The lattice vibration contribute the most to the heat capacity of solids. Lattice vibrations are the only contributors in non-magnetic insulators. Conduction electrons in metals and ordering in magnetic materials are the other contributors to the lattice heat capacity of solids. Here we will discuss only the contribution from the lattice vibration because the contribution of the electrons, as we have said, is extremely low. So this means that the contribution of lattice vibration is really very important, and we have to understand this, how it contributes to the heat capacity. Classical heat capacity. The energy of a solid in classical theory is expressed as E is equal to ES plus EV, where ES is the energy of the static lattice, while EV is the vibrational energy of the solid. The equipartition theorem of classical statistical mechanics assumes that each atom oscillates harmonically about its equilibrium position, and that the energy of one atom is given as the vibrational energy EV is equal to half of, that is, in the denominator you also have a m, 1 by 2m, px square plus py square plus pz square plus half k x square plus y square plus z square. So as you can see that the first part, that is 1 by 2m px square plus py square plus pz square, is the kinetic energy in the three directions, while half k x square plus y square plus z square is the potential energy along the three directions. Now, according to the equipartition theorem for a classical system in equilibrium, the average value of, let's say in the x direction, px square by 2m is equal to half kBt, where kb is the Boltzmann constant and T is the temperature. And this is also true for the other two directions, that is the average of py square by 2m and pz square by 2m would be similar, that is equal to half, each equal to half kBt. So the net total, that is the energy per atom at a temperature T, then is equal to E equal to Es plus 3 times kBt. So you see here that what we have done here is that we have taken the average of all these terms in the EV, and simply we add a ES also, as you see that in the first equation we had E equal to ES plus EV. So the sum total is E is equal to ES plus 3 kBt. Now the energy of 1 mole of the solid is then written as E is equal to E static plus 3 times Na kBt, where Na is the Avogadro number, which is equal to 6.03 into 10 raised to power 23 atoms per mole, while of course the Boltzmann's constant is 1.38 into 10 raised to power minus 13 joules per Kelvin. At T equal to 0, remember that E equal to ES, which does not include 0 point energy, since we are using the classical picture. So you know that in classical picture we don't have a 0-point energy, it is only in the quantum picture. Now it follows that the heat capacity at constant volume Cv is defined as the partial derivative of the total energy with respect to temperature at a constant volume. So consequently, if you apply this formula to the already obtained result for the total energy, you get Cv as equal to 3 Na into Kb. This is the famous Dulac-Petit law, which is valid only at high temperatures. As you can see that this particular value of Cv is completely independent of the temperature. The experimentally measured values of the specific heat is the Cp, which is at constant pressure, and not Cv. But since we are considering a harmonic solid, and fortunately Cp is equal to Cv in this case, the reason for this equivalence is that the difference Cp minus Cv depends on the square of the temperature coefficient of linear expansion, and this coefficient actually is 0 for a harmonic crystal. So you can see that immediately it's very clear that actually the expansion of solids occurs because of the anharmonic motion of the atoms, and this is exactly what we will actually study in more detail in the coming up modules. Dulac-Petit law, let us discuss this. What exactly is this? It's a classical law. Now, according to the Dulac-Petit law, the specific heat at constant volume, that is Cv, is independent of temperature, but measured value of the heat capacity Cv approaches the constant value 3 times Na into Kb only at high temperatures. You see that here Na is the Avogadro number and Kv is the Boltzmann's constant. So what it basically means is that the Dulac-Petit law tells us that the specific heat is constant not only at low temperatures, intermediate temperatures, as well as the high temperature. It is constant, completely independent. But this is not exactly what we observe experimentally. We observe that it is constant, it approaches the constant value only at extremely high temperatures. So consequently, Dulac-Petit law is valid at high temperatures only and fails to explain the variation of the specific heat at constant volume Cv with temperature. And this is very natural because one would think that there's something to do with quantization. Now here, look at this figure. It's a plot between the specific heat and constant volume Cv versus the temperature. The solid line is the experimental curve, while the dashed line is the Dulac-Petit classical law. So you see here, clearly demonstrating the fact that it so much deviates from the experiments. It is not that you are simply measuring Cv at high temperatures. You need the values of Cv all throughout the low and the high temperatures. And the validity of this Dulac-Petit classical law is clearly valid. This shows that it is valid in the higher temperature range. It completely deviates in the intermediate and the low temperature range. In fact, as you can see that in this figure, at 0 Kelvin, the specific heat is 0, which is very natural. But unfortunately, the classical Dulac-Petit law fails to give this value of 0 Cv at 0 Kelvin. Now, this Einstein model of lattice specific heat, the Einstein assumed that these atomic vibrations are quantized. So this is basically, you see here that now we are introducing this slowly, the process of quantization. Here Einstein, what he did was he quantized the atomic vibration so as to explain the experimental observations that specific heat decreased as the temperature was lowered. Now, since lattice vibrations are quantized in this theory, the term phonon, heat capacity, can also be used. Why not? Because phonon is a term which is used for the mechanical modes at extremely low temperatures, which is quantum in nature, discrete energy levels. So we could say that it's a phonon heat capacity. To calculate the phonon heat capacity, one needs to know the average thermal energy. To this end, we have to calculate the average thermal energy within the harmonic approximation. And why the harmonic approximation? Well, In the harmonic approximation, you see that the anharmonic effect plays a very crucial role. So now what we are doing is that within the harmonic approximation, the atomic distance, the separation between two atoms, is not very large. It's modest enough so that we still have a crystal which is intact. And this is something which you will actually learn, that when we deviate from the harmonic approximation, then something very important happens. That what happens? The solid vibrates too much and then it can melt. The thermal expansion melts. So we are not going into that detail right now. We are simply assuming that the solid is still intact, it's not melted, the vibrations are small, so that the harmonic approximation is valid, and according to that harmonic approximation we want to calculate the average thermal energy and hence the phonon specific heat. If one assumes that the motion of each atom is described by a harmonic oscillator, then the allowed energy values are given by epsilon n is equal to n plus half h cross omega, where n is equal to 0, 1, 2, 3 and omega is the angular frequency of the oscillator. In this model, it is assumed that each atom vibrates with the same frequency omega. The average thermal energy of the oscillator epsilon in thermal equilibrium at temperature T is written as epsilon is equal to summation over n Pn epsilon n, where the probability Pn that an oscillator has energy epsilon n is given as the Boltzmann distribution. That is, Pn is proportional to exponential minus epsilon n divided by kBt. And since Pn is a probability, then obviously the summation over n equal to 0 to infinity over Pn will always be equal to 1. All probabilities, if we sum them, it will be equal to 1. So this means that a summation over n equal to 0 till infinity P exponential minus n plus half h cross omega divided by kBt, that is, what we have done is that we simply have substituted epsilon n as n plus half h cross omega. So this summation would be equal to 1, where P is a proportionality constant. So consequently, what happens that if we do a small analytic calculation from this expression, we will immediately find the value of this proportionality constant P is equal to exponential h cross omega divided by 2 kBt multiplied by 1 minus exponential minus h cross omega divided by kBt. So this gives us the final expression for the probability Pn, which is written like this, that is exponential minus n h cross omega divided by kBt multiplied by 1 minus exponential minus h cross omega divided by kBt. So substituting this expression for Pn back into the expression for the energy leads to the following expression, that is epsilon as a function of omega t is equal to 1 minus exponential minus h cross omega divided by kBt bracket closed multiplied by h cross omega multiplied by summation over n equal to 0 to infinity bracket n plus half bracket closed exponential minus h cross omega n divided by kBt. Now since summation over n equal to 0 to infinity exponential minus n h cross omega by kBt is equal to 1 divided by 1 minus exponential minus h cross omega by kBt, and the summation over n equal to 0 to infinity n multiplied by the exponential minus n h cross omega by kBt is equal to exponential of minus h cross omega by kBt divided by brackets 1 minus exponential minus h cross omega divided by kBt whole square. Taking these two useful expressions into account, this finally leads to the results, that is epsilon, which is a function of omega t, is equal to average of n plus half whole multiplied by h cross omega, where this average of n is called the phonon occupancy number and is equal to 1 divided by exponential h cross omega divided by kBt minus 1. So as you can see that these lattice vibrations are quantized the same way as radiation oscillators, and the phonon occupancy average of n is defined as the expected number of phonons in the energy state epsilon n of an oscillator in thermal equilibrium at temperature T. The internal energy of a lattice which contains n atoms can be written as U, which is equal to 3n h cross omega brackets average of n plus half brackets closed. Now if n is equal to Na, that is the Avogadro number, the specific heat is then written as Cv partial derivative of U with respect to T at a constant volume is equal to 3 times n kb and a function Fe, and this function Fe actually is a function of h cross omega by kBt. So this Fex is called the Einstein function and is defined as Fex is equal to x square divided by e raised to power x minus 1 multiplied by 1 minus e raised to power minus x. Together with Fex, we can actually now define an Einstein temperature. So what is the Einstein temperature? The Te is equal to h cross omega divided by kb, so that this Einstein function which we had defined, Fex is equal to Fe, a function of Te divided by T. That is, it's a ratio, the Einstein temperature divided by the thermodynamic temperature. In the high temperature limit, that is when T is much more than the Einstein temperature, x is very small, that is x is much less than 1. This gives Fex is equal to approximately 1 minus x square by 12, and hence Cv is equal to 3 Na kb in brackets 1 minus 1 by 12 Te by T whole square plus a large number of terms which we ignore. The expression for Cv in the Einstein model then agrees with the classical Dulop-Petit law at very high temperatures. That is, I mean, like if you take T is very high, so that this particular term in Cv, that is 1 by 12 Te by T whole square, is very small and almost equal to 0, and the Cv reduces to 3 Na kb, which is independent of the temperature. And also, as T decreases, Cv also decreases. This is something which was not there in the classical Dulop-Petit law. In the low temperature limit, when T is much less than Te, x is very large, and in this limit, Fex is approximately goes as x square into e raised to power minus x, and hence Cv is equal to 3 Na kb Te by T whole square into e raised to power minus Te by T. Even though the Einstein's model showed that Cv, that is the specific heat at constant volume, decreases with decreasing temperature, but still the low temperature behavior was exactly not correct. The experimental data actually showed that Cv is proportional to T cube at low temperature instead of an exponentially decreasing function as predicted by Einstein. So as you can see that even though the Einstein model converges to the classical Dulop-Petit law, and it also explains very well with the experiments at high temperature, it is unable to predict accurately the experimental data at low temperatures. So this is one of the major drawbacks of the Einstein model, though of course this was the first step towards quantizing solid partially, coming close to the true experimental data, even though that we should, I mean, sort of appreciate this Einstein model. Now, this particular figure which actually is displayed shows the specific heat for various models. So as you can see from here that in this figure it's a Cv versus temperature, and this dashed dotted line, which is a straight line in the top of the figure, shows the classical theory, which is the Dulop-Petit law, which is completely independent of the temperature. As you can see, it is a straight line. Also, in the complete lower portion, actually, it is also shown that this electronic heat capacity, the dashed line, so that is basically the contribution to the overall heat capacity from the electrons, which is substantially low as compared to the vibrational part. And also shown in the figure is the experimental curve, and the Einstein model also is shown. So you see that even though from the figure it is very close to the experimental result, but it is not exactly matching. The discrepancy is there at low temperature, which is very high, and the discrepancy, as we had discussed earlier, is basically because Einstein had only partially quantized it, in the sense that there were some errors in the assumptions that Einstein had taken, which we can state this now. Whereas one of the major unrealistic assumption of the Einstein model was that all the atoms had a common frequency, which is not true actually, because different atoms are in a different environment and it certainly cannot have the same frequency. The coupling forces within a solid tends to make the movement of neighboring atoms correlated. And also finally, that when we do not take all the atoms having a common frequency, then we have to take the help of the density of states. And the density of states theory will help to overcome the shortcomings of the Einstein model, which we will describe in detail in the next module. So students, let us summarize what we have learned in this module. In this module, we have studied and learned first the Dulong-Petit law of classical heat capacity. Well, second, what we have learned is the validity of the Dulong-Petit law. Well, we have learned that this Dulong-Petit law actually is not valid at intermediate and low temperatures. It is valid only at high temperatures. It's a classical law. It's grossly, it's wrong in the intermediate and the low temperature regime. Third, we learned is how to calculate the average thermal energy of a harmonic oscillator. Fourth, based on this, the Einstein model of heat capacity that we learned. So what Einstein did was he quantized the atomic motion, and as a result of which he could derive a better formula for the Phonon heat capacity compared to the Dulong-Petit law. And this Einstein model was able to explain the intermediate and the high temperature limits of the thermal heat capacity or the Phonon heat capacity. But of course, it still had its own drawback. Validity was also limited, but still better than the Dulong-Petit law. And finally, we learned that what were the drawbacks of the Einstein's model. Thank you.